2. So let's go ahead and start with this. Okay, so what we're going to do with this third example is we're going to take just a different function, and we're going to look at analyzing where it increases, decreases, and look at the concavity like we were doing last time. Okay, so really what you want to do is if you're asked to find increasing and decreasing, you do the first derivative. Concavity is the second derivative. So let's go ahead and let's review how you do your derivative on a natural logarithm. Okay, now this is a chain rule because you're doing a logarithm of a function. Okay, so the general rule that you know, what's the derivative of ln x? 1 over x. So see, it's different on this. What it is it's 1 over the function, but since that function is something different than just x, then you have to multiply by the derivative of what's inside. Okay, I think you had one kind of like this on the last homework. Okay, so what's the derivative of what's inside? 2x minus 4. Good. Okay, so let's write that then as f prime of x. You can factor a 2 out if you want to, but you don't have to. We will in a little bit, but not right now. So let's see, and then we have x squared minus 4x plus 5 like that. So that's our first derivative. Okay, and I'm just going to leave it like that. The bottom does not factor. It kind of looks like it would with a 5 adding up to 4, but it doesn't. And so I'm going to just kind of highlight that, and then we'll deal with that in just a minute. Let's go ahead and get the second derivative out of the way. All right, so when you do the second derivative, you got to do the derivative of the derivative. So how are you going to do the derivative of that thing?
Quotient.
That's a quotient rule. Good. Okay. So the quotient rule is going to go the bottom. You just write down the bottom as it is. Okay, then what do? You do the derivative of the top. So what's the derivative of the top?
2.
2. That's good. That's easy. Okay. Then what we do is we do it backwards, and now we do a minus sign on the quotient rule. So now what we do is we go minus, and we do the top, 2x minus 4, and then we do the derivative of the bottom, which is 2x minus 4 again. Okay, like that. Okay. Now what we're going to do is that's all over the bottom squared. So we just write x squared minus 4x plus 5 all to the second power like that. Okay, so that is your quotient rule. And we do need to simplify that out. Probably the best approach to doing this is just multiply out the numerator. I don't really see a common factor. I just multiply everything out on this and do this. So let's go ahead and do that. So we're going to take the 2 and distribute it. So we'll have 2x squared, and then minus 8x, and then plus 10, like that. So you want to do that. Now the place you want to be really careful with is right here because of that minus sign. Now you're going to need to FOIL the 2x minus 4 times 2x minus 4, but keep it in a parenthesis and then distribute that negative through there. That's a real common place where students often mess up. Okay, so let's go ahead and FOIL the 2x minus 4, 2x minus 4. You can go ahead and start that. So the first term is going to be 4x to the second. Outside term is going to be minus 8x. Inside term is another minus 8x. Okay, and then the last term is 4 times 4 is positive 16. Okay, and then I'm going to write that over again, the bottom square. Don't forget about that. Okay, and then we're just going to put together like terms. Okay, now I'm just going to right now just distribute the negative through like that. Everybody have a question about what I'm doing so far on the second derivative? Okay, all right. Okay, let's put all the like terms together. Now be careful about that distributing part here. So be sure you change all those signs. So you're going to have 2x squared minus 8x plus 10 minus 4x squared plus 8x plus 8x minus 16. Now you could collect like terms inside that parenthesis before you do that if you want to. It doesn't make any difference. And then I got all over the bottom square. Okay, so let's see what this leads us to then. Okay, it looks like we have several like terms we can put together. So I've got 2 minus 4 would be negative 2x squared. Okay, it looks like one of the 8x's crosses out. So it looks like I'm just left with an 8x. And then 10 minus 16 is minus 6. And that's all over x squared minus 4x plus 5 squared, like that. Okay, that's your second derivative. Now, you could factor a 2 out of the top. I'm not going to do that yet. Yes?
But those two 8x's from the original function, those would equal negative 16.
Yes, right here, that would be negative 16. And then it would change to positive 16. Now, what I did is I didn't collect the like terms before I distribute the negative. It doesn't make any difference. You can do it either way. You get the same thing. Okay, so that is our second derivative. All right, any question about the derivative part of the problem? Now, this is going to have a little bit messier function to deal with. So what we're going to end up getting into now is sign charts and stuff. So we're kind of divide my paper into two, and let's just do a sign chart for increasing. So the first thing we want to do is we want to find what we call critical numbers. Okay, remember, critical numbers occur in two places. It occurs where f prime of x is equal to 0 or f prime of x is undefined. Okay, so there's a couple of things on this that the bottom doesn't factor. But what I want to do on this is I want to do, what you can do on a rational function is you're just going to take the derivative, write down the derivative, and then set that equal to 0 and solve that equation. And then that'll get a critical number. You can do that in your head too. I mean, you can learn to do that in your head. Really what you're doing is you have an equation with a fraction. So how do you deal with that? You can multiply by what you're trying to get rid of, right? Okay. All right, so what you would do on this, I guess, is just multiply by x squared minus 4x plus 5, both sides, like that. And it turns out if you have a rational function, like we have here, you just set the numerator equal to 0. So what you would end up having then is 2x minus 4 equals 0, and then you can solve that equation. That's an easy equation to solve. You can even do that in your head. So that's 2x equals 4. Divide by 2, you're going to get x equals 2. Okay, so that is a critical number right there. Okay, now the thing you got to be kind of careful about on a rational function is it's possible that the denominator could be 0 somewhere else also, but it may not. Okay, now it looks like that doesn't factor because of that plus 5 there. I'm going to go ahead and I'm going to put this in the quadratic formula. Okay, students always kind of when I have to do the quadratic formula, but we have to deal with it every now and then. Okay, so let's go ahead and put it in and see if it leads us anywhere. It may not give us any solution. So that goes, remember, quadratic formula is negative b plus or minus square root of b squared minus 4ac over 2a. Okay, and let's see what happens on this one. So again, b is negative 4. Remember, you're looking at a is 1, b is negative 4, c is 5. Okay, you're looking just at the bottom because we're setting that equal to 0. That's the reason we're doing that. Okay, so that's going to be negative 4 plus or minus square root of b squared. Okay, that's negative 4 squared. 4ac, a is 1, c is 5, all over 2 times a, like that. Okay. So like I thought, we don't have a solution. That's what I was kind of hoping for, okay? Because otherwise we'd probably have to go to the calculator. So here's what I want you to see on this. Look at what's under the radical. That would be 16 minus 20, right? Okay, that's a negative number, right? So what you get is you actually get this. And you don't have to work out the rest of it. It's just you have 4 plus or minus square root of negative 16 over 2. That doesn't have a solution. So what that means is we're not going to get a solution out of that, so there's no place where the denominator is undefined. Does that make any sense why I'm doing that? If you got a rational function, you got to figure out where it's undefined, because we're dealing with a derivative, and if that was undefined someplace, those would be critical numbers also that we'd have to do in our sign chart. Okay, does that make any sense? Okay. All right, now we're ready to go through and do a sign chart. So what we need to do on that, you just want to typically draw a number line. The only critical number we have is x equals 2. So that's all we're going to worry about is x equals 2. Okay? Now what we have to do is we have to do test points. You can always use a calculator a little bit if you want to on this. So we're plugging into the first derivative, and the first derivative is what I'm highlighting there, okay? So let's do that. Give me a test point below 2.
0.
There you go. That's the one to use. 0 is the easiest number to calculate with. So you would have 2 times 0 minus 4. Then you'd have 0 squared minus 4 times 0 plus 5. Now all you care about is whether that's negative or positive. That's all that matters. If you look at that, it looks like you get negative 4 for the numerator over 5. So that means you're positive like that. Okay? Everybody see what I did?
How is that positive?
Oh, I have no idea how it's a positive. I meant to say negative. Okay. All right. That's why you guys are looking at me weird. Okay, so that's a negative. Now, what does that mean if the first derivative is negative?
Decreasing.
Means the function's decreasing, right? Okay. So we know that we're decreasing. So we can go ahead and write down that we are decreasing from where to where? Negative infinity to 2. So we know that without a doubt. Okay. All right, now let's go with the test point for 2. What do you want me to use?
3.
Yeah, 3. Okay. So we're going to do 2 times 3 minus 4. That's a positive numerator. That's all I care about. Then I have 3 to the second minus 4 times 3 plus 5. So that looks like 6 minus 4 or 2 in the numerator. You can do this in your head. 9 plus 5 is what? 14 minus 12 is 2. That's positive. Okay, that's what you care about. Okay? All right, what does that mean to you? That we're increasing. Okay, so the function's increasing. And from where to where? 2 to infinity. Okay, we have that down. Okay? Now, the other thing that we want to kind of look at here is the concavity, but we can also look at it whether we have a min or max. Okay, what do we have here? The function's decreasing, then increasing. What does that tell you? Okay, we don't know what it look. We just know it's decreasing and increasing, so that means we got a minimum. So we have a local minimum at, let's just write x equals 2. We can get a point on the calculator if we want to. How about a max?
No.
You don't have one. Okay, so we have that. Okay, now what makes this problem a little more complicated than the ones I did in the last class is the derivatives are more complicated. Okay, so you got a little bit more room for error, so you have to be kind of careful on that. Okay, any question about that? Okay, first derivative is not very bad on this particular problem. Second derivative is a little harder. So now what we're going to do is you're going to work with the second derivative, and that's how you analyze your concavity. Okay, so we'll have to see what happens on this. So what we have to do is we have to set it equal to 0. So I'm going to do this kind of at the side. And what you can learn to do, if you want to do this, you can. If you're dealing with a rational function, this saves you a little time, not much, but a little bit, is if you set the whole thing equal to 0, like this whole function to 0, all you're going to do is multiply by the denominator to get rid of that. So you can just set the numerator equal to 0. Does that make sense? This isn't the last problem. Look what I did. I set it equal to 0. I multiplied by the denominator. It ended up, I was just looking at the numerator. So that's all that matters. So what we need to do is we need to solve this equation. The other thing is we already figured out that the solution of x squared minus 4x plus 5 is there's no solution. So that denominator has no solution. So that's not going to provide a place where this function's undefined. Okay? If the quadratic formula gave us a couple of numbers, then yeah, we'd have to use that in our sign chart. Okay, does that make sense? Okay.
But where
Now,
would you use it in the sign chart though? Like
just somewhere in there. I mean, you'd have to put them all in order. So like if you got 2 on this last problem, say you got 5 and 6, well, you just put them in order. And you still break it up into intervals and use test points.
Test each of those.
Yes, you have to test each interval. Right, so there will be times when your function's going to be undefined somewhere. Okay, this one, does it have a common factor? Let's hope it factors. Maybe it does, maybe it doesn't. Okay, we can take a 2 out. Now what I'm going to do is I'm actually going to take a negative 2 out. To me, that makes the factoring easier. You don't have to, but I'm going to choose to do that. That's going to change the sign. So that's going to be x squared minus 4x and then plus 3 like that. So it does factor, thankfully. Okay. All right. So we have that. Okay. Now what you can do with this is the -2, you can divide by that. Okay. I mean, that's okay to divide, but you could have even divided the whole problem by -2 before you factor it if you wanted to. Okay. So now what it turns out that this thing factors, you got to solve that by factoring. So you're going to have this. You're going to have x and x. 3 times 1 to get 3. How do you make 3 and 1 become -4? Minus minus, right? Okay, so you got that. Everybody see that? Inner terms -3, outer terms -1x. They come together. Okay, so that's right. So, in your head, what's the solution to that equation? 3 and 2. Okay, so that means you have critical numbers at x equals 3 and x equals 1. So we have 2 critical numbers now. Okay? Everybody with me on this? Okay? Don't forget about the denominator. If the denominator was undefined somewhere, if it was 0 somewhere, we'd have to use that in our sign chart. Okay, now go ahead and make yourself a sign chart. Okay? And then what you want to do is you want to do x equals 1 and x equals 3. Okay, like that. And then we're going to plug into the second derivative. Now, I want to show you something on this that's kind of helpful. I'm going to use like 0 as my test point here. Now, this is real helpful. It'll save you time. Look at the denominator. The denominator is something squared. So no matter what you plug in for x, what's going to happen? You're going to get a positive, right? So you don't need to test that denominator. You need to just realize that it's a positive denominator no matter what I plug in. So you're just dealing with the numerator, okay? So what we can do on this is you can just plug into this numerator. You could use the calculator to help you a little bit if you want to, but it's pretty easy if you use 0. So you would have -2 times 0 squared plus 8 times 0 minus 6. What kind of number is that? Negative. 0 plus 0 minus 6 is negative, right? That's -6. That means you have a negative numerator, right? Okay, so what's a negative divided by a positive? Negative. Okay, that means it's a negative. What does that tell you about the concavity? We're sad, concave down, okay? So that means you are concave down, okay? All right, the denominator is positive, but if I plug a 0 into that numerator, it turns out to be negative because the zeros just kind of cancel out. Okay, let's take 2, see what we get there. Okay, so we'd have -2 times 2 to the second plus 8 times 2 minus 6. And you can just try to process this in your head if you want to. It looks like I have 4 times -2 is -8 plus 16 minus 6. So that looks like that's a positive. Okay, so it's a positive over a positive, so it's a positive. What's the concavity? Concave up, you're happy, okay? All right, now we got one more to do. Let's use 4. We already know the denominator is positive, so plug in just to the numerator of this second derivative. So that's -2 times 4 to the second plus 8 times 4 minus 6. So that looks like -2 times 16 plus 32 minus 6. Okay, that looks like that's negative because that's -32 plus 32 minus 6. Okay, so that means you're negative, which means you are concave down again like that. Okay? All right, you guys see what I'm doing? A lot of arithmetic. You can use your calculator to help you, but most of the time you can do that in your head pretty well. Okay, where am I concave up? What's my interval going to be in my answer? 1 to 3. Okay, how about concave down? -infinity to 1, and then what? 3 to infinity. Okay, what is a point of inflection? It's a place where the concavity changes. Did the concavity change?
Twice.
It changed twice, doesn't it? Okay, so you would have a point of inflection at 1. Now let's just put x equals 1, just the x value. If I want you to put the point, you can get that on your calculator if you want to. And then x equals 3. Okay? And then let's go back before we finish this problem. Let's just look at this on the graphing calculator. And let's see if it looks like we've done everything correct. Okay, we didn't even touch the calculator till the end. And that's the way you ought to do these problems. You know, you can kind of use the graphing calculator to help you make sense of what you just did. Okay, so put in, you'll need to clear that off. We'll just start in the standard window. You want to put ln, and then x the second minus 4x plus 5, close the parentheses, and then you can just go zoom standard. Okay, and let's see if that gives a good enough viewing window to see if we look right on this then. Okay, there we go. Okay, I'll slide this to the side, and then we can kind of look at this graph here a little bit and compare it to everything we got here and see if this looks okay to us. Okay, so let's see. What did we find? Increasing from 2 to infinity. Does that look good? Decreasing from negative infinity to 2. Does that look good? Minimum at, what do we get? X equals 2. Does that look good? Okay. All right, and how about concavity? Whoa, that's kind of a hard one. Let's see, concave up. That's real hard to see on this too. That's why your graphing calculator is not real good to rely on, but it's there if you zoomed in. What you're going to find is your concave down from negative infinity to 1, and then your concave up just for a little bit from negative 1 to 3, then your concave down again. It almost looks like it's down and down, but it isn't. Actually, this is not a sharp point. The derivative does exist there. So it's actually doing more like this, where you have an inflection point, kind of does something like that and like that. You'd have to zoom in on your calculator to really see that well. The calculus doesn't lie. Okay, we're 100% right on this. Okay, but looks can be deceiving. You see what I mean? Okay, how's that look to everybody? Okay, impressed? Okay, all right. Okay, let's go to this next thing here, and let's do some graphs. The next thing I kind of like you to be able to do, this is really an activity that sees if you know the meaning of the symbolism that we're learning. Let's get those two computers away, please, and let's today, please, let's get our notes done. Okay, you got your notes? Well, still, I mean, I don't know. There could be Facebook on there for all I know. Okay, or they could be my math lab homework. Do that at home. Okay, so let's see if we can get this figured out. Okay, so what we're going to do is we're going to draw a graph on this, and when we do this, just go ahead and just draw yourself a coordinate system. You can just kind of sketch that. Now remember, what we're doing is a possible graph on this. So first of all, when you have this statement, what does that tell you about your graph? It says that you're increasing. Okay, boy, I must have missed some information. I didn't give you enough information on this. Okay, so what I needed to do on this was tell you where you're increasing on. So let's add to that. Let's say that f prime of x is greater than 0 at, let's say, 2 to infinity. And let's see if I can make this work okay if we do it that way. Okay, all right, so let's just go to 2. And let's just kind of make a sketch to ourselves that we are, we're increasing somehow. We may have to adjust that in just a minute. Okay? And then let's say that, what is the second derivative if it's greater than 0? What does that tell you? That means you're concave up. Okay? So let's just say that we're concave up. Let's keep it simple and say 2 to infinity also. Okay? Like that. Okay. So if you were doing that, well, then what you would have to do is there's only one way you could really draw this graph. You have to think about concave up looks like this. You can either have this. You could have a shape like that. That's concave up. You could also have a shape like this. Or you could have a shape like this. Okay, but what has to happen is it has to be increasing and concave up. So which of these would it look like? Which one are you pointing at? This one, hopefully? Yeah, it has to be like that. So what you'd have to have is something like this. You'd have to say, okay, we've got a point there and doing that. Now, beyond that, who cares? I didn't give you enough information to tell you what's going on there. So I mean, who knows? It could do something like that or whatever. That's kind of optional. But the key thing is you would have to have a shape kind of like that. Where you make the y value, that doesn't matter. Okay, it's just that you have identified from 2 to infinity you're increasing in concave up. Okay, does that make sense? I left off that 2 and 2. I left something off of that, so otherwise you couldn't do anything on that problem. Doesn't make any sense. Okay, all right. So the other way you could kind of look at this, I could also say something like if I said on negative infinity to infinity, and that may have been what I meant, then your graph would just look like that. It'd be always increasing and always concave up. That's the way it'd have to look. Okay? All right, let's see if we can figure out the next one here. Go ahead and read the information, and let's see if you can put this one together then. Now, what I want to do on this is just kind of review what these things are, and then I'll see if you can give you a chance to try to put it together yourself. Okay, the statement that I just highlighted, what does that tell you?
Increasing.
Okay, so we are increasing from negative infinity to 0. We're going to have to draw a graph that's increasing from negative infinity to 0.
Would it be decreasing? Decreasing.
Oh, decreasing, sorry. Okay. I don't know why I put that there. Okay, yeah, it's negative. It's decreasing. Okay. Thank you. Okay. What does the f double prime less than 0 tell you?
Concave down.
Okay, you're concave down, so you're going to also have to be concave down there. Now, one thing that'll kind of help you when you're processing this, if you're concave down, there's 3 possibilities. You can look like that, you can look like that, or you can look like that. Okay, you'll have to figure that. I'll give you a chance to figure that out in a minute. Okay, now the next thing, I'm going to highlight this. What does this tell you? Okay, that's going to tell you, again, you're decreasing, right? Okay.
Concave up.
But you are concave up because the second derivative is positive. Okay, from 0 to infinity like that. So whenever you're kind of putting these together, concave up, there's 3 possibilities. You could have a U shape like that. You could have half of a U shape like that. Those are the possibilities. Now, see if you can put together a possible graph. And everybody's graph will look slightly different, but you should have the same shape like that. So you got to think about, okay, there's 0. You want to be decreasing and concave down. And over here you want to be decreasing and concave up. So think about that for a minute and see what you can figure out. Okay, put something on your paper. What we want to do next here is kind of look at if you have information about a derivative, being able to do a graph on this then. Okay, so this is kind of, I took this out of the book. This kind of shows you how you could put stuff together. So if you knew you had these 2 pieces of information, the first derivative is negative, so it's decreasing, and the second derivative is positive, so you're concave up. Well, you'd have to draw a graph like that, wouldn't you? That's the only way to make the graph decrease and be concave up at the same time. Okay. Then if you moved on, here's another one. This would say first derivative's positive, that means you're increasing. Second derivative's positive, that means you're concave up. So you'd have to draw a graph like that. Does that make sense? We've already done that a little bit. And then why would this be a local minimum? Well, because you're changing from decreasing to increasing. So anytime your sign chart has a change in it, then you would have either a min or max. Yeah.
Would that also be the inflection point?
The inflection point will occur where the concavity changes. Now this is still concave up, right? Okay. So you're going to have an inflection point right here because the graph changes from up to down like that. Okay. So basically, I'm just kind of reviewing what we did. This would say your first derivative is positive. What does that mean? Increasing. Second derivative is negative. That means concave down and so forth.
So inflection only occurs when the
concavity changes. Okay. Only if the concavity changes and if it's a point on the graph. So for instance, if the concavity changes but you're undefined at that point, then it can't be a point of inflection. That's another thing that can happen. Okay, I mean you could have something like a function that looks like this with a bubble. That's possible. This right here would be concave down. This would be still, whoops, that's a bad example. Let's do something kind of like this. let's say that you were concave down like that, and then let's say you changed to concave up, and let's say you had a bubble there. Well, the concavity changed, but it's not a point of inflection because it's not a point. That's the idea. That's another thing that can happen, see. Okay? Okay, so let's move on and kind of look at...
Question on that.
Yep.
So what if it was like came to a point and it was like how you have, I guess never mind, it'd still be concave down.
Yeah, the concavity doesn't change, but you might be getting at where you have a sharp point,
Yeah,
kind of like you could be concave up. Let's see, you could do something kind of like this. That's actually something that would be possible where you'd be concave up and concave down. Well, that would be a point of inflection. Even though the derivative doesn't exist there because of the sharp point, it's a point.
Okay.
So it's got to be a point on the graph. You have to be defined on the function in order for it to be a point of inflection.
Okay.
That's what you got to focus on. Okay, so let's move down to this now. I want to work with couple of more illustrations of this, and then we kind of wrap up with one business application. This one won't be as hard. So let's go ahead and work on this then. So we're going to just start with critical points increasing and decreasing. Okay, this one should be pretty simple because it's a polynomial. What's the first derivative? Go ahead and work that out. 12x to the fifth minus 12x to the third. Okay, and we're going to do concavity on the next page, so what do you need to do?
Do the derivative of the derivative.
Derivative of the derivative, second derivative. So what's that? 60x to the fourth minus 36x squared. Okay, we got that. Okay, now this one's probably a little simpler than the one I did a few minutes ago. Now what you do if you're going to find your critical points, what are you looking for? You're looking for where the derivative is 0 or undefined. Okay, so what you want to go ahead and do now is write your derivative down, set it equal to 0, and then let's go ahead and solve that. So how does that factor? You can take a 12x to the third out, right? So that's going to leave you x squared minus 1, right? Does x squared minus 1 still factor? It's the difference of two squares. It goes x plus 1, x minus 1, so you might as well go ahead and do it. Okay, or you could set x squared minus 1 equals 0 and solve, but you got to be careful about this. You're going to get 3 critical values on this problem. Okay, so I'm going to go ahead and you can factor that as x plus 1, x minus 1, and then you can set that equal to 0. Okay, now you can do this in your head. What are the 3 critical values?
0, -1, 0, 1.
Good. 0, -1, and 1. Okay, so we want to write that down, -1, 0, 1. Okay, like that. Okay, everybody okay so far? Okay, when you got polynomials, it's generally pretty easy to do. Okay, now we're going to do our sign chart. So you can go ahead and get your sign chart built here. Okay, when you do that, you want to get all of your critical numbers on there. So we have -1, 0, and 1. Then we do this. Now I'm going to do something totally different this time, okay? But because I've done enough sign charts, okay, you guys were having a little bit of trouble with that graph of the first derivative. Here's what I want you to do. This might help you guys. And actually, you can do this some on your homework. It'll save you time and it'll help you understand things better. So what I want you to do is put in your first derivative. Okay, graph 12x to the fifth minus 12x to the, whoops, doing that wrong. Okay, and just do it in the standard window, and you probably will get a good enough picture to fill in your sign chart. So we have minus 12x to the third. What in the world am I doing? I'm not even getting this right. It's because of that exponent thing. Okay, so now minus 12x to the third. Okay, graph it in the standard window if you haven't already done that by now. Okay, zoom 6. Okay, and when this graph comes out, that will give me the sign chart. Now I'm going to change this window a little bit just so I can see it a little bit better. So I'm going to change, like, say, -5 to 5 on x. You don't have to, though, because you might have a good enough viewing picture anyway. Okay, so here's my graph. Now I'm going to slide this to the side. Where did it go? There it is. Okay, so let me show you kind of what happens, and this is a real nice thing to catch on to. Now see, that derivative gives you your sign chart. Your sign chart is staring you right in the face. Okay, what's happening? What kind of values does the derivative have right here?
Negative.
Negative, there you go. Negative derivative. What does that tell you? Function's doing what?
Sloping down.
The function's decreasing. Don't confuse that with derivative. What's happening to the derivative here?
It's
Positive values.
Positive values, okay? Okay, then what? Negative values. Then what?
Positive values.
See what I mean? That's the derivative, okay? That's just what its function values are. If you still don't understand it, check this out. You could go to your graphing calculator. You could look at your table. Look what's happening. See how the derivative is changing from negative to 0 to positive. If you go through that, that's telling you how the signs are changing. Okay, does that help any? I hope it does, because a sign chart, a graph of a derivative gives you a sign chart. Okay, you can do that too. If you're getting a pinch on your homework, you can do that. Sign charts take a little bit of time to do, but you can do it fast that way. Okay, so anyway, what does that tell you? It tells you you're decreasing, increasing, decreasing, and then you're increasing again like that, so you're ready to write your intervals. Okay, so your intervals of increasing are going to be what?
-1 to 0.
-1 to 0,
1 to infinity.
and 1 to infinity. Decreasing, -infinity to -1, 0 to 1. See, I graphed the derivative on the calculator. That's another alternative approach, and it helps you too if you do that. Okay?
That makes pretty much this first section way easier.
It does, doesn't it? The sign chart's not hard, but it's tedious sometimes. So if you do just graph your derivative, you're going to see the sign chart.
So you
Okay.
really, when you do it like that, you don't even have to test.
No, you don't have to test because it's doing it for you. I like you to know how to do that both ways to see how the test points work and everything. But yeah, you can do it this way. You can graph a derivative and you get it fast that way. Okay? All right. So that takes care of that. Now let's work with the concavity. Okay?
What were the critical points?
What's that again?
What were the critical points?
The critical points? The critical points occurred where the derivative was 0. So that was on the graph. The critical points would occur here, here, and there. It would be everywhere the derivative is 0. So the critical numbers we got were what? I forgot. -1, 0, and 1. That's where the derivative is 0. Okay? Like that. Don't confuse that with the function. Remember, you're looking and analyzing the derivative. So that might help a little bit. Okay? Okay, now let's go on to the concavity. Okay, so let's see. What our second derivative we already did, that was,
60x to the fourth.
what was that? 60x to the fourth,
That's 36.
and then minus 36x to the second. Okay, so now we're going to go to the concavity. Okay, what is a common factor you can take out?
12x squared.
Okay, that's good. Or, so you're going to set that equal to 0. So you can take 12x squared out. So that's going to be 5x to the second minus 3. Okay, that's your factoring there. What do you do with it? Set it equal to 0. You got to find critical numbers. Okay, that's defined everywhere. So you want to take 12x squared times 5x squared minus 3 equals 0, and you want to solve that equation. You're going to get into some square roots on this one, which is pretty typical. That happens. So you have two factors. 5x squared minus 3 doesn't factor, but you can still set it to 0, and you can still solve this. So if I have 12x squared equals 0, what's the solution to that in your head? 0. If you forget how to do that in your head, sometimes students do, you divide by 12, you get x squared equals 0, square root both sides, so you're going to get 0. Okay, so in your sign chart, you're going to use 0 as a critical number. Okay, now if you do 5x squared minus 3 equals 0, well, what do? You isolate x squared, and then you do the square root. So you need to move the 3 or add 3 to both sides so that you have 5x squared equals 3. Then you divide by 5. Okay, so you would have x squared equals 3/5. And then you'd have to take the square root of both sides, getting ahead of myself here. So we'd have x squared is 3/5. Square root both sides. Now don't forget, you're going to get a, good, you got to have a plus or minus. Don't forget that. Okay, so what you have is 0 plus or minus 3 over 5. Root 3 over 5 are going to be your critical values to analyze the concavity. Okay? All right. Now, let's do this, okay? Again, for something different, go ahead.
So real quick, that would be 3 critical numbers, right? 'Cause
Yes.
The second one is plus or minus?
Yes. Yeah, you got to have that plus or minus because you did the square root of both sides. Okay, let's make a sign chart. So we're going to have a 0. You're going to have a positive square root of 3 over 5. And you're going to have a negative square root of 3 over 5. Okay, like that. So what we can do here is this, okay? Now, you could do test values. Now, if you did test values, let me show you kind of what you'd want to do here. First thing you'd probably want to do is you'd want to go work out the square root of 3 over 5 and just kind of get a decimal on that. So that's about let's just say 0.8. Okay, this is about 0.8, and this is about negative 0.8 like this, okay? So now, I want to kind of save you a little bit of time on this now, kind of begin to do that a little bit. So, you can do test points and plug them in to the first derivative, or the second derivative if you want to. Here's another approach. Let's do it on the calculator this time. So now what you want to do, what do you want to graph? The second derivative. Right, so let's put in 60 x to the 4th minus 36 x to the 2nd. I keep doing that. I keep forgetting about that exponent. So it's 60 x to the 4th. And get out of the exponent and then go minus 36 x to the 2nd. Okay, like that. Do a zoom 6 if you want to. And you may have to zoom in on this one a little bit, and I'm going to do that. I get kind of a W shape, so you can do this if you want to. You can go zoom in, which is option 2. You just do that and enter, just so you can see it better. Okay, by looking at the graph of that, how's the sign chart going to go? Tell me.
Positive, negative, negative, positive.
Plus, minus, minus, plus. Okay, does everybody understand what I'm saying? Yeah, you catch on to this, you save a little bit of time because, you know, doing test points is easy, but it's time consuming. Again, all this is going to mean is you have positive derivative, negative derivative, negative, 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 plus, 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 okay? That's the value of the derivative. So, yeah, your sign chart's going to go plus here. It's going to go minus here, and plus there. Now we're talking about concavity. Now these are your critical numbers right here. That would be the, right there, that would be the square root of 3 over the square root of 2. That's what that'll be. So now you can answer the concavity and you got it made, okay? So it's going to be concave up here and there, and it's going to be concave down there and there, like that, okay? So what are we going to say for concave up? What's the answer? And go ahead and use the root. Don't use the 0.8. Just use, say, negative root 3 over 5, and then union root 3 over 5, comma, infinity, like that. Concave down. Now, concave down, you have to break it up into 2 intervals on this, too. So you want to say negative root 3 over hold on, like this. Negative root 3 over 5. Kind of forgot that root there. 0, union 0, and then positive square root of 3 over 5, like that. Okay, do you have any points of inflection? Your sign chart will tell you. How many points of inflection? How many times did the concavity change?
2.
Twice. Where did it change at?
Negative 3/5 and
right.
Negative square root of 3/5 and positive.
Right. Now don't look at your graph. That'll confuse you on your concavity. This is the concavity of the function. Okay, so you would have a point of inflection, and let's just write x values. You could even say plus or minus root 3 over 5, like that. Okay, so that's how you put the whole thing together then. Okay, Now, what we want to kind of do from here is see if we can put together a graph without the calculator. I don't want you to get too reliant on the calculator. Calculator is a great tool. It's a great learning tool and everything. But let's see if we can put this whole thing together without the calculator. That's kind of the goal here. And then we can use the calculator to check. So let's draw an axis. And let's see, I'm going to, really what I'm going to do is just kind of look at these, look at the sign chart. I'm going to take a snapshot of this so I can refer this as I'm going over this. Okay, and let me take a snapshot of this. What we're going to try to do is get this whole thing kind of put together here. Let's see what we can get put together. Okay, so let's see what we have. Now let's start by looking at, don't look at the concavity yet. Let's just look at the sign. The sign chart for increasing or decreasing is going to tell you roughly how your function goes. So what's it going to do? It's going to decrease, then it's going to increase, then it's going to hit a high point, then it's going to decrease and increase like that. I mean, that's what your function's probably going to look at. Now, if you look at the concavity is saying you're concave up until you get to this point. Now, at that point, when we did this, that was about negative 0.8, wasn't it? Does that look like that would kind of be concave up from here to there? Mm-hmm. Yeah, okay. Then we were concave down from there to 0. Does that kind of look like it's concave down? Mm-hmm. Then it looks like it's concave down a little bit more. And if you look at this second sign chart, that was positive 0.8. Okay, so that's pretty well how this graph's going to look with your two inflection points like this. So you're decreasing, increasing, decreasing, increasing, and then you're concave up. That looks good. Concave down. You can put those two intervals together for concave down, and then increasing or concave up like that. So that would be a good sketch. Now, the only other thing that I would probably want you to do on this, let's see, we do have our maxes and mins, so what I would do with this is just kind of label like this. This is negative 1, here's 1 here. Let's just kind of put negative root 3 over 5 there. And then somewhere in here, that would be like root 3 over 5 like that. That's pretty close to 1. So then you could draw a sketch. Now you could get your minimums and maximums. You could get the y values of that from your calculator if you want to. So I'm going to do one more thing. I'm going to have you go all the way to the original function. I do want to do this kind of by hand here. So f of x, this is what we're graphing, is f of x is 2x to the 6th minus 3x to the 4th. Okay, now let's go ahead and find the values of the mins and maxes, and then we'll be very accurate on this. Okay, so we had a min where? We had a min at negative 1, we had a max at 0, and we had another min at 1. So let's just evaluate those points real quick and do that. Now you can use your calculator on this too if you want to. F of negative 1 is 2 times negative 1 to the 6th minus 3 times negative 1 to the 4th. Okay, so that's going to be f of negative 1, that looks like that's 2 times 1, or 2, minus 3 times 1, so that's going to be negative 1. So that means you're going to have basically this. You're going to have a min at the point, negative 1, negative 1. Now what am I doing? I'm plugging into the function to get that function value. Okay, and if you take, a negative 1 to an even power, you're going to get a positive. Does that look okay? I didn't write every step on the arithmetic. I did some of it in my head. Is that okay? Okay, now let's do f of 0. So if we do f of 0, we just go to the function. 2 times 0 to the 6th minus 3 times 0 to the 4th. What's that in your head? 0. So that means we have a max at the point 0, 0. You need to get that accurate. You need to get the min and max. You need to figure that out to get a good graph. Okay, the last thing we're going to do is 1. So we're going to do f of 1, which might be negative 1 again. I think I can tell it is because this is what you call an even function. So if you work out the details on that, you're going to get, again, 2 minus 3 or negative 1. So that means you have a minimum at 1, negative 1 like that. Okay, you guys know what I'm doing? Okay, so I'm just plugging into the function. Don't get confused. When you're getting a function value, you go all the way at the beginning to the function. Now we're ready to put it all together. So what we're going to do is we have a minimum at negative 1, negative 1. So let's just put a dot there. You have a max at 0, 0. You have a minimum at 1, negative 1. And then you can sketch it like this. It doesn't have to be perfectly accurate, but you're going to be concave down, then the concavity changes. Concave down, concavity changes. That's what your graph looks like. Okay, now that's really accurate, actually.
And to find mins and maxes, you're only using the first derivative.
Yes.
Okay.
Yeah. So what I kind of did is really you get your graph mostly from that sign chart of the first derivative. You can kind of tell what it looks like, and then you can tell the concavity matches up. All you're kind of adding in there is those points of inflection, and that's where the concavity changes from down to up and up to down. Okay, problem solved. What do you think? It's a lot of work. Okay, part of the purpose of this is to help you understand how the calculus works, and it helps you understand functions better. That's part of what you want to do for, for higher things you're going to study, is get the concepts down. A lot of what we do in math is activities that help us with concepts. Okay, so let's go ahead and take our 10 minutes. All right, now this one's probably a little bit more complicated than the last one because it's a rational function. So what our goal is on this problem is to be able to graph it, get a good sketch of the graph without having to do anything on the calculator. And that kind of helps you do this to help you understand how functions work. If all you ever do is just put stuff in a machine, you may not understand anything about it. So we want to use the calculator at the end to kind of verify that we're correct. Okay, so first thing we want to do is we want to look at asymptotes. Now when you have a rational function, like you do on this, you have asymptotes. So the vertical asymptote, you guys remember how to tell where a vertical asymptote is? It's where the denominator is not 0. So what you want to do is you want to go ahead and factor this. Let's just go ahead and start by factoring that denominator. That denominator factors is x plus 2, x minus 2. That's a difference of 2 squares, so you want to get that down. And the numerator is going to factor as x plus 3 times x minus 3 like that. So we're going to get all of our asymptotes. We're also going to get intercepts this time. I don't think I put a blank on here for intercepts, but I want to add that in there. Okay, so what you do, if you're going to find a vertical asymptote, the reason I factor first, I want to make sure nothing doesn't cancel out, because if something cancels out, it's not an asymptote, it's a hole. That's something we learned about. So we don't have that. So we not want to just take that denominator. I've already got it factored. Set it to 0, so what are the asymptotes? X equals 2, x equals negative 2. So we got that. Okay, when we do our graph, we're going to have that. Okay, horizontal asymptotes. So let's see if you remember anything about that. Okay, so I'm going to multiply this out. You don't have to, but I'm going to. The numerator is 2x to the second minus 18, like that. Okay, can you guys tell where the horizontal asymptote is just by looking? 2. Y equals 2. Remember what we learned is we learned if the degree of the top and bottom are the same, which is 2, the degree is the highest exponent, then the horizontal asymptote is the ratio of what we call leading coefficients. Those are the numbers in front of those highest powers. So we say y equals 2. So we got that. Okay? So we've already got that piece of information. Now, as we get information, we'll kind of begin to put this together at the end when we do our sketch. Let's go ahead and go all the way down to a couple of pages to, go to the page, skip the next page, and let's go ahead and start our sketch. We're just going to get the asymptotes together. Our goal on this is just to sketch this 100% without having to rely on our calculator. Okay. All right, so let's see what we got here. Did I write that horizontal asymptote right? Yeah, okay, so, yeah, we have 2 and negative 2. So what you want to do here is just put a vertical asymptote at x equals 2. Okay, put another vertical asymptote at x equals -2, and then we have the horizontal asymptote is going to be at y equals 2 like that. Okay? Well, that's a start. Okay, we got to have all that information. That'll kind of help you a little bit with that. Okay, so let's also do intercepts while we're at it. I think that's another thing we want to be sure that we do. Okay, so let's add this in. If you do an x-intercept, what you really do is you set the function equal to 0. So you set, or you let, f of x equal to 0. Because that's what an x-intercept is. It's a place where, it's a point where the y value is 0. Well, actually what you can do on this is if you solve this equation, I'm trying to try to get you to kind of save you a step here. If you set the function equal to 0, how are you going to solve this equation anyway? We're going to get rid of the fraction, right? You're going to multiply both sides by x squared minus 4. And see, I want you to just know how this works in your head, because if you multiply by x squared minus 4, aren't you just going to end up with the numerator equals 0? Does that make sense? Okay, so you can just set that numerator equal to 0, because you can get the fraction to go away. All right, how do you solve that? You solve it by factoring. So we have, you can factor that. So what are the two answers to that equation? 3 and -3, right? Okay, so we have x-intercept. It would be -3, 0, and then we'd have 3, 0 like that. Okay? If you have a rational function, that means a ratio of polynomials, fractions. Set the numerator equal to 0, that's how you get your x-intercepts. Okay? Now, go down to your graph and just go ahead and put a dot on both of those places. Okay? So we now have an intercept at 3, and we have one at -3. Now see, just doing that helps you significantly to do that. Okay, so we got that. All right, everybody got that? Now it's something you need to know how to do. X-intercepts are found by setting the function to 0. The reason that works is because of this. Okay, that y value is 0. That's why we set it to 0, is because of that. Okay, then we have this other one is -3, 0 like that. Okay, now let's do a y-intercept while we're at it also. Okay, so y-intercept, what you do is you set x equal to 0. Okay, let's go ahead and do that. So you go to the function I gave you. You're going all the way back. We haven't even done any calculus yet. You're just going to replace everywhere you see an x, you're going to put in a 0. So you're going to have 2 times 0 squared minus 9 over 0 squared minus 4. Okay, that looks like that's 2 times -9 over -4. That's -18 over -4. That reduces to +9 over 2. Okay, that's about, I think, what is that, 4.5, 4.5. Okay, so your y-intercept would be the point 0, 4.5, like that. Have you guys done that before? I don't think we've done that much in this class, but it's something that you're doing when you're doing curve sketching, is you want to know how to find intercepts. And this is the key thing to have down, is what you do. The opposite variable goes to 0 and you got it. Okay, go to your graph, and on the y-axis, go up to 4.5 and put a dot there, and then label that as 0. That was 9/2, 4.5. Okay, so we got our intercepts. And see, by doing this, I already kind of have a good idea how this graph's going to go. I mean, it's probably going to go like this, because it always has to, when it hits a vertical asymptote, it goes either to infinity or negative infinity. That's got to go there. It can't do anything else. What's going to happen here? It's going to level off at the horizontal. Right here, and it's going to kind of do the same thing. It's going to go down to negative infinity and then level off. Okay? Now, what happens here, we don't know. It could go like that. It could be concave up. It could be concave down. It could do all kinds of things. So we're going to do the calculus to kind of figure out the rest of this, but you really could already got a pretty good picture of how this goes. Okay, so now let's go to the next page. Now we're going to work on the calculus part of this. So let me write down the function. So the function is 2 times x squared minus 9. And then it was all over x squared minus 4. Okay, I got to do a derivative. Tell me how I'm going to do that. Quotient rule, okay? Now, I'm going to go ahead and just multiply this out. I just think it might be easier to do the derivative of the top if we do it like that, okay? Now, you got your quotient rule. So,
Wait, is that 18?
no, 18. Let's not do that. Actually, I would have lucked out on my derivative probably, but that's, thank you. Okay, so we've got bottom derivative of top minus top times derivative of bottom over bottom squared. You don't have to write that down. I'm just kind of reminding you what that is. Okay, so let's go ahead together and get the quotient rule going. Okay, so we have the bottom, x squared minus 4. What's the derivative of the top?
4x.
4x, good. Minus the top. What's the derivative of the bottom? 2x. What do you do to the bottom? Square it, bottom squared. Okay, so we got to do that. Now I want to get everything in the product or the quotient rule, and then probably the best thing is just multiply it out. That's what I'm going to choose to do. You can factor like a 2x out of that. You can also do it that way. Maybe I'll do it that way because students sometimes have trouble with that. But you have two choices. You can distribute, multiply, or you can factor out. Okay, I'll do the factoring because I think you need to practice and work on that a little bit. See, what you have is you could take a common factor of 2x out, right? You could, if you wanted to. Okay, so let's do that. If you take a common factor of 2x out, okay, think about what you're going to be left with, okay? Well, okay, if you take that out, you're still going to have an x squared minus 4 here, but what else do you have to have? Got to have a 2, right? Not a 2x, but a 2. Now it checks. Okay, now the next one, just kind of take that out. What's left? 2x squared minus 18. Okay, then it's all over the bottom square, like that. Now you don't have to do it that way. You can multiply out and you're going to get the same thing I'm going to get anyway. But that's helpful to learn how to do that. Okay? All right, now let's multiply out, collect all of our like terms in the numerator, and see if we can get this simplified. So that's 2x. Distribute the 2 through. That's 2x squared minus 8. What happens to this thing right here? I'm asking because students always mess up here. Change the signs, right? When you have a minus in front of parentheses, be sure that you adjust those signs correctly. So how's that going to go? Minus 2x squared plus 18. Okay, then it's all over the bottom squared like that. Any questions so far? Quotient rule gets kind of messy sometimes. Okay?
So the 4x and the 2x, you just simplify that?
Well, this part right here it is. Whatever's left here in the parentheses in the bracket, I'm going to do that. Now see what I did, and you don't have to do it this way. You could just do like 4x to the third minus 16x, and you can distribute. But what I did is I took that 2x out. And when I do that, then you're going to have that, and then 2x times 2 is going to give you the 4x. That's the factoring. If you take that out, then you're just left with that. What I'm working on right now is simplifying inside the bracket. Okay, that's the idea. That's the algebra going on. Okay, the 2x squareds cross out. Okay, so what you have is a 10. Now I'm going to do this in my head, so make sure you follow this. 18 minus 8 is 10, right? Then what do? 10 times 2x is 20x. Okay, everybody okay with that? Saves a step. Okay, I like to try to be careful about that when I'm teaching though. Okay, so now we're ready to do a sign chart that will analyze where the function's increasing and decreasing. So it's going to go like this. Remember, what we're looking at is where the derivative is 0 or where the derivative is what? Undefined. Okay, now this is pretty important. So if you set the derivative equal to 0, you can do this in your head. Okay, the way that you actually do this is you multiply both sides by the denominator. You don't have to write that down because you can do that in your head. So what you get is you get the equation 20x equals 0, right? Okay, so what's the answer to that? 0. Okay, so you have a critical number at x equals 0. Okay, again, that's the same thing we've been in over and over again. Set the derivative to 0 and solve. Okay, now here's the next thing. Now here's our derivative right here. Is there any place that derivative is undefined?
No.
Look at the denominator. Is there anything that makes the denominator 0? 2? What else? Negative 2. Remember, we have asymptotes at negative 2 and 2. At the beginning of the problem, we had vertical asymptotes. We are undefined there. Okay, so you can also do this. If you set the denominator equal to 0, and I'll go ahead and solve it and show you how you would actually do this if you don't know how to do that in your head. You got to figure out what makes the denominator 0. Well, here's what you could do. You could square root both sides. You would get x squared minus 4 equals 0. Then you could factor. So you would get 2 and negative 2. So you also have critical numbers at 2 and negative 2. Okay, so we are undefined. The derivative does not exist at 2 and negative 2. You know why? Because the function's discontinuous there. There's asymptotes. Does that make any sense? Okay, so we don't have a derivative at those vertical asymptotes because we're discontinuous. So what we're going to do now is we're going to make a sign chart. I'm not going to do this on the calculator this time. I'm just going to go ahead and crunch it out the way I originally taught you. So let's see. We have a critical number at 0. We have negative 2. And we have 2. And then we want to go ahead and put this together. Okay, so what we're going to do is we're going to plug into this derivative. Okay, now there's something that's real important on this. You know, I want to save you guys time. What's going to happen to that denominator? If you plug anything in for x, what's going to happen? You're going to get a positive, right? Take advantage of that. It'll save you time. So we know that the value of the denominator of that derivative is positive. Okay, we know that. Now, just plug your test points into the numerator. So if you do plug negative 3 in, and do this in your head, if you do 20 times negative 3, you get a negative, right? So what's a negative divided by a positive?
Negative.
And that tells you the function is decreasing, right? Okay. Let's take a test point here. Let's use negative 1. Well, you do 20 times negative 1. That's negative. Means the function's still decreasing, right? Okay. Move on to the next place. Let's use 1. Plug into the numerator. What's happening? Therefore, we are what? Increasing. Okay. Then out here, you got 3. Plug in. You got 20 times 3 plus like that. So you're increasing like that. Okay. Now I did that real fast, but you're going to, with practice, you can do that pretty fast. You already know the denominator is positive. Does that make sense to everybody? All you care about is the numerator, so we got that. Okay, so we're ready to write everything then. So let's see. We had our critical points were negative 2, 0, and 2. We're going to increase. We do got to break this up into 2 places because we do have a asymptote there. So we're going to say 0 to 2 and 2 to infinity. Decreasing, we got negative infinity to 0. No, negative infinity to negative 2. And then union negative 2 to 0 like that. Okay, so that's it. All right. Now, let's go onto our graph, and let's see if we can kind of begin to figure out how this is going to go. So, decrease, decrease, increase, increase. Okay, that's what we got. Okay. Before we do the concavity, let's just go ahead and do that. Okay. So, like I said, I think I already kind of knew how this was going to go. If this thing is decreasing from negative infinity to, what did it say, to negative 2, well, wouldn't the graph have to do something like that? That's all it could do, because it always goes to infinity or negative infinity around a vertical asymptote and levels off like that. So that's your decreasing. Then it also said, what, decreasing again. Then it said increasing. So what's going to happen here? If it decreases, then increases and increases, what's going to happen in between the asymptotes? Yeah, it's going to have to do something like that. And I bet when we do the concavity, it'll show that. So I suspect it's going to do that. Okay, increasing, what's the next one going to do? It's going to have to approach the asymptote, go through the intercept, and level up. Now, we didn't even do the second derivative, but That's probably what the graph's going to look like. We're going to do the second derivative. So how's the concavity going to turn out on this? What's this? Down, up, down. Okay. Do you have a point of inflection? That's a good question.
No.
The concavity does change from down to up, but that's not a point of inflection. Why?
It's undefined.
Yeah, it's not a point. Okay, it's undefined. You don't have any points of inflection. The concavity does change, though, but since you're undefined, you don't have one. Okay? Okay, let's go ahead and do the concavity and just do that. So, and we're really verifying on this. So let's see. The first derivative is 20x over x squared minus 4 to the second. Okay, so we're now going to work with the second derivative. Okay, so this looks like a quotient rule again, so we need to go ahead and put that in the quotient rule. Second derivatives can get messy sometimes, but this one shouldn't be too bad. Okay, so we're going to do the bottom. I want to go ahead and write the bottom. Derivative of top. Derivative of top's what? 20. Then do it backwards, minus the top. How do you do the derivative of the bottom? Chain rule, right. Okay, so be careful. Okay, you're going to bring the 2 down, leave the x squared minus 4 alone to the first power, then what? Derivative of what's inside, which is 2x. Okay, that's chain rule. Now you've done that. You've done some homework on that too. Okay, that you can think of that as extended power rule is another way to think of that. And then you're going to do the bottom squared. So we're going to take that and then we're going to square it again like that. Okay, so I've got bottom, derivative of top, minus top, derivative of bottom. Does that make sense? You got a chain rule inside, built inside of that quotient rule. Now what I'm going to do on this is I'm going to clean it up a little bit. I'm just going to write this first piece right here. I'm just going to bring it down and write that as 20 times x squared minus 4 to the second. The second piece, there's several things I can multiply. I've got 2 times 2 is 4, times 20 is 80. Then I have x times x is x to the second. Then I've got x squared minus 4 to the first like that. Okay, 20 times 2 is 40, times 2 is 80, x times x is x squared. Now, tell me what the bottom is. If you square and then square again, what do you get? Fourth power. Okay, remember you multiply those x powers. That's algebra stuff. If you had x squared to the second, that's x to the fourth. It's because 2 times 2 is 4. So that's going to become x squared minus 4 to the fourth power like that. Now we need to simplify this thing. We don't want to go to no sign chart. We're not ready to figure out critical points now. Now I want you to look carefully on this because this is the algebra that sometimes students struggle with. Those are the 2 terms. Okay? Those are the 2 pieces of the problem. What do you see that's in common? You have a 20 and 80. What's in common for 20 and 80? 20. What else?
X
X squared minus 4 to the first. How come? You take the lowest exponent out. So you want to take a 20 and an x squared minus 4 out. Watch this carefully because sometimes this gets into some background issues. So we're going to put a 20 and an x squared minus 4 to the first, then draw a bracket, and then just kind of figure out what you got left over. Okay, what do you multiply this by to get what's in the first box?
X squared minus 4.
Right, x squared minus 4 to the first, right? And you got to make sure you're right on that. Every time you make a move, multiply it out in your head and make sure you're right. Okay? Now, what do you multiply this by to get this?
Minus 4.
4. What else?
X
You
squared.
need an x squared. Anything else?
Negative.
That's it. Okay, and you didn't need the minus, right? So you have minus 20 times 4 is 80. You need the x squared, and that's it. Okay? You got to verify that in your mind. So it's basically 20 times 4 is 80. You have an x squared, and then you have this. You have everything you need. Okay? Now what?
Cancel.
Got some canceling. Good. Okay, there's going to be a couple of things you can do on the simplification on this now. So what will happen with this is, this whole thing's to the first, so you don't really need those parentheses, so you can cancel these 2. Those are like terms. So when you put that together, you would have 20 times x squared minus 4 to the first. And then this would be 1 minus 4 would be negative 3 x to the second minus 4, like that. And then I'm kind of in a factored form. There is one other thing that you can do. Do you see that?
You can cancel the x squared minus
No, one of those cancels, doesn't it, right? So if one of them cancels, what's left down there? 3 of them. There's 1 there, 4 there, there's 3 left over. Okay? So what you would end up having for your second derivative is you would have this 20, one of those cancels out, leaving a third power. So you have x squared minus 4 to the third. Then you have negative 3x squared minus 4 like that. Okay, that's our simplified second derivative. See, that gets messy.
Could you show me how you did the negative 3x squared minus 4 real quick again?
Yes, okay, that came from here. Just look at this part here. Okay, what I did was this is 1x to the second minus 4x squared. See, that's a first power, so it's just itself. 1 minus 4 is negative 3, and then you have the minus 4. Okay? All right, now here's what we're going to do to finish this up then, is you're going to take this second derivative and you're going to set it equal to 0. Now, if you set it to 0, now again, this is a rational function. If you're going to solve this equation, all you would do to solve this equation is multiply by what you're trying to get rid of, right? So you would have the numerator equal 0. And then this is actually easy to solve. So what you'd want to solve is 20 times negative 3x squared minus 4 equals 0. Then you can solve that equation. Now, it doesn't factor, but you could do this. You could divide by 20. Then you would get negative 3x squared minus 4 equals 0. Okay, how do you solve something like that? Well, you isolate, take square root. So you can move the 4. Boy, I hope I didn't make a mistake on this. Oh, never mind. No, I didn't make a mistake on that. Okay, I thought I was thinking of something. Now I'm okay. You're not going to get an answer on this, which is okay. We still have critical values, and I'll explain that. So what we have is x squared equals negative 4/3, but when you take the square root, you get no solution. Now that doesn't mean we don't have any critical values. It was good to try that, because remember, a critical value occurs 2 places: where the derivative is 0, so that doesn't happen, but where it's undefined. Is this derivative ever undefined? Look at the denominator. What makes the denominator 0? 2 and negative 2. So we do have 2 critical values. See, we are undefined at 2 and negative 2. Well, what did we find happened in our graph anyway? We had asymptotes. So the second derivative is never 0, but it is undefined in 2 places.
So it being to the third power doesn't matter?
Doesn't make any difference. Okay. Because, see, if you solve this equation, this is really what you would do. You would set it equal to 0. Then you could take a third root of both sides.
Gotcha.
And then you get the same thing. Okay? All right, so here's how your sign chart goes. Okay, so what you would have is you would have negative 2. You're undefined there. And then you're undefined at 2. Okay, then you could do test points on this again. And what would happen on this, without going through too much of the details on this, you could use negative 3, 0, and 3. Now you would plug into the second derivative up here. And what you would find on this is, and I'm just going to tell you what you would find because I don't want to go through all the arithmetic, but if you plug negative 3 into this derivative, and if you worked that out, you should get some negatives. I'm just saying if you did, okay? All right, if you plugged a 0 into that derivative, what you would end up getting on that is you would get positives. Okay, you guys see what I'm saying? I'm not going to take the time to do that just because it's time consuming to work the arithmetic out. If I plug the 3 in, I'm going to get a negative. Well, how did I know that? Well, because I know what the graph looks like, see? Okay, so this means you're concave down, you're concave up, and then you're concave down. Okay, like that. So what you would end up having, that would kind of put everything together for us then. So we would have concave up would be negative 2 to 2. And then concave down would be negative infinity to negative 2, and then 2 to infinity, and we don't have a point of inflection. Okay, even though the concavity changed, the thing is you're undefined where it changed, so you don't have one. Okay, what's the hardest part of that problem? Probably the algebra. You get right down to it. I mean, that second derivative can get messy with the algebra when you're talking about rational functions. Okay, okay, let me finish up with point of diminishing returns. The very last problem on that I'm just going to let you do on your own. I'll just have you do outside of class so we can have a little bit of time to talk about our test. So what I want to do is just do this problem with point of diminishing returns. And I'm not going to do all the stuff with increasing and decreasing, because I'm mainly going to use the graph to kind of explain what a point of diminishing returns is. So I took this out of the book because it has a nice graph on it. So this basically is saying that X is how many TVs you're selling, and then the store invests X $1,000 in an advertising campaign like this. So if you graphed this function, I want to just have you go to this next page and let's take a look at this so I can explain what the point of diminishing returns is, okay? So what's happening on this function is this basically. What's happening here is your derivative right there is positive and it's getting bigger, right? Okay, your slope of your tangent line is getting bigger, right? But what happens here is something kind of special. The tangent line right there is like almost at a 45-degree angle. And if you're at 45-degree angle, the derivative is 1. Now what's happening? Isn't it kind of sloping, leveling off again? So what's happening is the function clearly is increasing everywhere, right? Okay, so if you did an analysis of where it's increasing, it's going to be from there to there. Okay, if we did the derivative and did that. But what a second derivative is it's telling you how the first derivative is changing. Okay, so let's think about that. That's what I was showing you. But my pen is representing the derivative. Right now the derivative is 0, but the slope is getting bigger. So that means the second derivative, when you did your sign chart, would say that that's concave up. Okay, then what happens here is it starts slowing down. So the rate of increase is always changing. Okay, that rate, but what happens right there is then the slope starts leveling off. Does that make sense? Slope gets bigger, slope gets smaller. Okay, that's an inflection point. That's what that is. So what you're doing on a point of diminishing returns is, although your function is increasing there and continues to increase, it starts slowing down. Okay, so that's the idea, is it's a second derivative. You're looking at concave up and concave down. You can see that okay? That's concave up. Then it starts being concave down. Okay, so let's work out a couple of things on this to kind of go over this. Let's go back to that previous page. Mainly what I want to do is just work with the second derivative, because I've kind of summarized everything in the second page anyway. So let's go ahead and do the first and second derivative. Okay, so if we do that, we're going to have 9x the second, and then that's going to be 4 times 0.5 is 25 is 1, x the third. So that's your first derivative. Okay, the second derivative is 18x minus 3x to the second, like that. Okay, now what we're going to do is going to make a sign chart for the concavity. This is how you do a point of diminishing returns. So what we're going to do is we could do the increasing and decreasing. I'm not going to take the time to do that though. Let's set that equal to 0, solve the equation, and then find that point of inflection. Okay, how do you factor this? It looks like you can take a 3x out, so you'd be left with 6 minus x is equal to 0. Okay, now you're going to set each factor to 0, so you'd have 3x equals 0. Then you'd have 6 minus x is equal to 0, like that. So this would give 0, and then this one would give x equals 6. You can do that in your head. So those would be the two places where the second derivative is equal to 0. Now in this problem, they've given you a domain that X, which is the investment of X $1,000, it's going really from $0 to $9,000 for your ad campaign. So if you did a sign chart, you would go from 0 all the way up to 9, and then you would have this critical number right here. That's a critical number, that's a critical number right there, okay? So then if you did test points on this, so let's do like 1 there, and let's do like 7 there. So you can plug in either here, or you can plug into the factor. I always think it's easier to plug into the factor. So let's just plug in. This is easy to do. So you'd have 3 times 1 times 6 minus 1. That's a positive result. What would that tell you about the concavity? Concave up. Plug 7 in. Let's plug it into the factored form. You'd have 3 times 7 times 6 minus 7. That's a negative number, so what's that telling you? Concave down. So what's happening is this right here is an inflection point, and in the context of this problem, okay, what it's saying is it's a point of diminishing returns, because what's happening is the rate at which that number is increasing changes at that particular point like that, okay? So you would have a point of diminishing returns at 6. That's a pretty easy one to analyze with the function. That's a pretty easy derivative, okay? So let's go to this and just kind of wrap it up, and we'll talk about our test. I'm not going to do the last problem. So what's happening on this problem is this is like dollars. The x-axis is dollars. And if you read the problem, N is how many things you're selling. So this is like, that would be like 800 TVs, okay? And that's the cost of the advertising campaign right there. So what's happening on this is the dollars you're spending continue to increase, but then once you get past $6,000 in your ad campaign, what happens is the rate at which your production of TVs is beginning to decrease. So what's happening right here is we call that diminishing returns, because the rate starts changing. Does that make any sense? Okay, so that's an inflection point. That's what the point of diminishing returns is. Okay, so that's your diminishing returns. Okay, slope changes its rate. Concavity changes. Okay, that's one of the things that we use that for in the analysis of business, is diminishing returns. Okay, so that